everyone, and welcome back to the industry track. Our last section here is dedicated to aerospace and defense applications. And our first set of speakers join us from NASA and the Jet Propulsion Lab. So I'd like to invite to stage Allison Park. Allison is the Deputy Technical Fellow of Materials and Additive Manufacturing at NASA. She's part of the office of the Chief Engineers Group called NASA Engineering and Safety Center. And I will let her continue on and further introduce herself when we get started. And the other person I'd like to invite up to stage is Sarah Leumen. Sarah is part of NASA's Jet Propulsion Lab, and she is an additive manufacturing engineer there. And her responsibilities focus mostly on research projects and parameter development on laser powder bed fusion systems. So with that, ladies, I will let you take it away.
All right, mic check. Melanie, can you hear me?
We can hear you great.
All right, and then I'm going to be sharing. All right, I'm full screen. Can you see me?
Yes, it looks great, Allison.
Yeah? Melanie, can you see?
Yep, it looks great.
Okay, great. Hi, everyone. My name is Allison Park. Thanks for joining, and thanks for the wonderful organizer who put a lot of work into this. I'll be joining by Sarah from JPL. I'll start off the presentation, and then Sarah will join about 10 minutes. Okay. So everyone here, some of you are already familiar with all the exciting things that's going on around NASA and, just in team space in general around the world. But it is very exciting time right now with a lot of activities going on around the Earth orbit. We're getting ready to go back to the moon with eyes on Mars. So starting with International Space Station, we just celebrate 22 years of operation this year. We work with a lot of international partners to build the space station and keep operating. A lot of accomplishment throughout the whole ISS program, but I think in my mind the biggest thing coming out of that is the start of the true commercial space. So we have cargo flights as well as cruise space flight that are being done by commercial companies. Cargo, we have Northrop Grumman and SpaceX delivering stuff to ISS. And then, of course, cruise spacecraft by SpaceX and soon to be Boeing. So a lot of things happen with ISS program and the commercial spaceflight. In the launch vehicle, both in civil and commercial and military, we had a historical year last year. I heard that we break the record of launch to orbit last year. So a lot of things going on there as well. The new space station that we're going to be starting up with, again, with a commercial space model. That's also very exciting for us. But that's stuff that's going around Earth orbit. Like I mentioned, we are going back to the moon with our space launch system. That's gonna carry astronauts in Orion spacecraft. It's not gonna go directly to the moon. We're gonna have a pit stop at another space station that's orbiting the moon called Gateway. That's gonna be pit stop, fueling station, staging area, so that we drop off stuff and then we take additional stuff to the moon. Before we send a human back to the moon, we're gonna use our commercial lunar lander system to deliver cargo and stuff that we need to kind of build the base there, as well as robotic surface mission. So we're going to be doing all that in less than 4 years. And again, We have eyes on the Mars. Eventually, want to go to the Mars. We have been doing awesome robotic exploration activities managed by JPL. So that's also exciting about what's going on here. So like I mentioned, less than 3 years, you're going to be observing. You're going to be part of this back to the moon, we call it Moon to Mars program mission. You're going to be seeing a lot of commercial companies delivering instruments and payload and tech demos to the lunar surface. You're going to be seeing the commercial companies delivering stuff to be building the gateway station. And then finally, you're going to see human landing system, human landers landing on the moon that will take the astronauts to the base. But that's not the most exciting thing. So exciting thing is that we're gonna the boots on the moon. You hear the expression. We're gonna have women's boots to go back to the moon. We're also gonna have the first POC astronaut back to the moon. This picture is from a graphic novel that NASA made, and it's free to download on the website. It illustrates a fictional character who is a woman astronaut going back to the moon, of course, with a sidekick. His name is RT. So if you have little kids out there and you haven't seen this, please spread this. Okay, so I wanted to tell you all that because yes, there are a lot of programs, there are going to be a lot of missions, but how are you guys implementing? Are you guys looking into additive? Are you guys implementing additive? Are you guys fully embracing the advantage of AM? The answer is yes to all of them, right? We know the key advantages of AM especially on rocket propulsion hardware that additive gives. That includes lead time reduction, cost time reduction, and part count reduction, as well as we can embrace going for new design from scratch using additive that will give some or a lot of performance benefit opportunities. And just using AM in just typical development cycle, the design fail fix cycle, additive can give you the benefit of doing it faster. But we understand the challenges as well, especially at the end of the day, you have to deliver the hardware that's high value and must meet the performance, right? You're taking this hardware to deep space, and you probably going to have one or maybe two chances of doing that. So we have to get it right. So we understand those challenges. As far as I see, I'm from NASA headquarters, so I get to see a lot of different missions, a lot of different programs, a lot of different commercial partners and contractors bringing the AM hardware to us. So I get to see a lot of those. And I think NASA has kind of dual roles in as far as additive manufacturing goes. And it kind of mirrors how NASA is organized as well. So as you know, we have our research center like Langley, Glenn. Then we have our flight center like Kennedy and Marshall Space Flight Center that concentrates on operational program, getting the spacecraft off the ground and do the missions in space or deep space. So additive manufacturing kind of follows, kind of mirrors those two attributes of NASA as an agency. So in one hand, we spend a lot of time and money and resources in the pure research and development effort with the goal of, hey, we want to make sure that we do this right so that we can kind of share the knowledge across the industry outside of agency so that they can adapt and kind of industrialize this AM. So we have a lot of project in that area. On opposite end, we have, like I mentioned, we have flight programs that are operational or about to be operational. Those programs, they need to be made sure that the additive AM hardware that's in the spacecraft, especially in propulsion system, because that's where a lot of additive applications are right now, we need to make sure that the AM hardware is fit to fly, basically, so that it can meet the safety and mission objectives. I mean, at the end of the day, that's the goal, right? So today I'm gonna be talking about the first bullet. I'm gonna be more focusing on how NASA's AM tech development activities kind of look like. I'm going to give you some example of stuff that we have been doing in rocket propulsion area. And then Sarah from JPL will come to the stage, and she's going to be talking about how her AM part turned out to be really good candidate to show how you qualify per NASA's internal AM standard. So I'll start with mine. Go to next. Okay, so over the years, I mentioned that we spend a lot of time and resources to look into different additive technologies. And sorry, I'll be coming from more metal AM perspective. So just keep that in mind. So we've been doing our own investigation, evaluation, and tech maturation of different AM technologies like you see here. And we've been watching others do it, either our commercial partners or our typical classic contractors, or just in industry in general. And from my perspective, I see a lot of people struggling how to pick the right AM process for your end application. And my colleagues, someone mentioned in the reference, we had the same thought. So we decided to write a journal article. It's under review right now, so you can look for it when it comes out. But basically, the goal of this journal article is that we want to provide the context of the entire AM lifecycle consideration, the attribute criteria, and discuss practical trade factors when you have a decision to make which AM process will be good for your end application at the end of the day. How do we do it? What are the attributes of process and material selections? We try to use our real life firsthand experiences, stem from our own mistake and our own experience, and heavily rooted in liquid rocket engine applications. So hopefully that will be a reference point for all of you guys. So I mentioned liquid rocket propulsion system. So again, it's mostly metal-based and mostly based on laser power bed, as well as direct energy deposition, both using laser and EB, and both using wire and powder. We use different metal alloys, nickel and iron-based alloys, because we like the strength, we like the high temperature capability, we like the corrosion and oxidation resistance. So there are a lot of those in the rocket propulsion. Copper alloys, especially in thrust chamber application, where you need a good thermal conductivity and good is able to handle the thermal flux within the chamber. So we use a lot of copper alloys for the chamber application. For the turbo pump, which is on the right box of you, a lot of components that's in the turbo pump system, we like to use, of course, nickel and iron-based alloys, as well as titanium aluminum for the housings. box in the middle, you see the rocket nozzle, the bell-shaped nozzle that we are trying to use DED, powder DED application, as well as wire. So and in the bottom, you can see we're not just making one-off part and do nothing. We want to show the whole life cycle of how AM hardware is designed, manufactured, and verified through hot fire testing. So you see the smoke and fire. A lot of testing is done at our Marshall's Flight Center, at our test stand there. And of course, the big engine we are testing at our Stennis test center. Okay, so you might want to ask me, okay, so I see you guys are using a lot of additive, but does it really make sense? And show me the data, right? So here it is. My dear colleague of mine, he presented this at a conference last year, and this is based on his real life hands-on experience. We took one of notional LOX methane rocket engine, and we took the component in the thrust chamber assembly, the main combustion chamber. You see in the picture there. Think about combustion chamber. If you talk to combustion devices people, they'll say that's the most important part in the whole rocket engine. But it is, because you're making the combustion gas that's coming out of the injector, and you are shooting out as fast as you can out of the nozzle to essentially lift up from the earth, right? So it's pretty important. But traditionally, how we've been making this, again, this is not that big of chamber because it's only 35K pound-force thrust level engine. But typically we start with billet. In this case, it's a copper alloy billet to make the line. Eventually, you're gonna be forged and machined into a liner, and then we put channels in. We call it slotting operation. We put channels in so that the copper liner does not get hot during combustion process. So we feed some or all of the cold propellant gas into the channel on the backside. So we go through the slotting operation, and then eventually joining, welding, brazing operation to complete into a final main combustion chamber. So that's how it's traditionally made. The schedule and cost number that we put it here, that's again based on our own experience internally. It clocks at 18 months and 310. When we first decided, okay, how can AMB really stand out here in terms of schedule reduction and cost reduction, and then having the same performance or better. So we didn't want to go full on with AM. So we did, and plus we were limited by the laser powder bed machine size back then. So we made into 4-piece assembly, printing into 2-piece, again with copper alloys. But this case, no slotting process needed because we printed the channels integral to the liner, right? So that way we were able to show the reduction in schedule as well as cost. But we didn't stop there. On this one, we still need the structural jacket that goes around the copper liner. So that one was an added process. But we also use an additive process, EB wire DED, to kind of clad the jacket on the copper liner. Okay, so that's the initial AM development. The next thing we did was we were able to print the entire thruster because, again, the powder bed laser technology mature and the machine size limitation was essentially gone. So we were able to print the entire thing with one piece. but we still need to put the jacket around the liner. And in this case, we ended up using laser powder DED process. So by doing so, again, we were able to use the schedule and cost. So this is just one example of how we are showing the benefit, the cost and schedule reduction benefit of AM. And this is only one hardware, and it happened to work for this, right? But I can also show you the example of where it did not work, right? A lot of reasons, right? Some technical, some programming reason, and some bad luck. So I just want to, make sure that it's not just all rosy. Things happen too. All right, so this is my last chart. I just want to cover what other things that are going on around NASA, around the agency. So I mentioned, definitely combustion chambers and a lot of combustion devices, components, injector, nozzle, ignition system, etc. But also we're targeting the turbo machinery, sub-assembly as well, the valves, the lines, all the ducts. We're looking into polishing, surface enhancement within the channel as well as the bulk. We're also looking at multi-alloy solutions and also multi-AM process solution for some of the components. And of course, we have very strong alloy development group around the agency. So we're looking into new alloy development, either refractory for very high temperature, very extreme environment like hot oxygen or hydrogen, and very low temperature because we are using cryogenic propellant for the rocket propulsion.
Hey, Allison, thank you so much for giving your presentation. We only have about 4 minutes left in this session, so I wanted to see if we could pass it over to Sarah and
Sure.
let her go through some of her use cases. But thank you so much for sharing.
No problem.
Melanie, do you think I should use the time to just answer some of these questions here?
Do you want to talk just a little bit about some of the projects that you worked on briefly, Sarah, since I didn't read your whole bio, and then, we can just jump into the question.
Okay, let me share my screen. Okay. Can you see my screen, Melanie?
Yes, it looks great.
Okay. I'll just go over this slide since we don't have too much time. A little background on this part. We designed a cable bracket for the Europa Clipper mission. And we went through the flight qualification with NASA Standard 6030. And these were some design considerations or lessons learned that I found along the way that are really important to consider as you go to qualify flight parts. So the first one is fixturing. This part, since it was organic, was really challenging to machine. So we ended up using this kind of dental putty, like what they use to make a retainer for you, and covered the whole part in that, and then took it to our mechanical inspectors. They did an optical scan of it to help the machinist locate the datums, and then they machined it from there. So what we learned in this instance was how important it is to involve the whole team ahead of time and as early as possible. And we did include the machinists and mechanical inspectors early on, but just getting their hands on the part, so much more came up. So I think having people involved in the prototyping process, bringing parts to them, all of that can be really helpful in making things run smoothly later. In the future, I think maybe adding some sort of sacrificial datum or flat surface that you could butt the part up against you would definitely save a lot of time and energy in that effort. Another consideration to think about as you're planning a flight part is GD&T. Again, since it's organic, there's not really natural datums. So this is a spot where you can talk to a lot of different people and designers. There's not too much literature out there, but there is some guides that have been written For this part, we ended up dividing the surface profile into sections. So the surface profile was tolerance just within its section rather than the whole part, which kind of saved us some room since additive parts do move often. And then lastly is schedule. I'm sure all of you have had experiences with schedule in the past, but I'm going to bring it up again. The schedule, we know with additive is a really fast process, the build process. However, all the post-processing can add so much time. So when you're making your schedule ahead of time, definitely consider the post-processing as well. And like someone mentioned in their talk yesterday, getting everybody realistic expectations can save you a lot of headache later. And with that, I'll put up my contact information. Let me know if you have any additional questions. And we can move into some of these questions from the chat if we have time.
Yes, Sarah, go ahead. If you want to pick one or two of the questions, that would be great.
Okay. I see Sam's here. What's the largest barrier to increase adoption at NASA? I think the largest barrier probably is heritage. A lot of the parts that are used have so much heritage, and the risk posture can be lower overall since NASA generally has a lower risk posture. So the way that we've been trying to fight down that barrier is with these standards. So like the NASA standard 6030 outlines how to get a flight qualified part, and it makes that possible. And then also just once it is done, then people learn that it's possible. So I think, heritage is the largest barrier, but we're working away at that one. Some other questions. And then another challenge here, another question about the challenges, material dimension tolerances. The materials can be a challenge since there isn't specifications outlined for all the materials yet. So that's another thing that we're working at is getting test coupons done so the designers can have something to base on, because a lot of times it's similar to the material wrought, but it's not the same. And that can be a hurdle for the designers because they are concerned about the change in the properties due to additive.
Well, thank you so much, Sarah. Thank you so much, Allison.